This is review of lecture 29, part 3. So here I'm going to give you an example of non-full rank matrix. So this is an example that Professor Strang gives in the lecture. And he tackles it in really a unique way that he just grabbed the one row and one column as the basis and make it orthonormal. But here let's try to do the normal way and see what will happen. Okay, so we compute the A transpose A as usual. So we will have 4386, which will be equal to 80, 60, 60, 45. Okay. Now we already know that this matrix is singular, so this is not full rank, so this rank is only 1. Therefore, one of the eigenvalue will be 0. So let's call it the eigenvalue 2 is 0, and the other eigenvalue is of course just the trace of it minus 0. So the first eigenvalue will be 125. You can also do it the old way by minus lambda identity, but I guarantee you will end up with the same values. Okay, now let's try to find. So we have it here, the sigma squared, actually what we have here, because we get it from the A transpose A. So our sigma 1 is square root of 1 to 5, and sigma 2 is still 0. Okay, so let's keep that in mind. Cool. Now we need to find the eigenvector of A transpose A, which will be our V. Remember, because A transpose A is the V sigma squared V transpose. Okay, let's keep that in mind too. Okay, so here we just do it one by one for the first lambda or sigma here. Let's use lambda because I'm talking about this specific matrix, right? So the first lambda 1 to 5, and the second lambda is 0. So my matrix will end up with 145, 60, 60 minus 80, and I want to find here x1 0, and I can do some division in the first row and second row. Then I end up with this one. My x1, which also will be my v1, is v3, and when I normalize them I get 0.6, 0.8 and 0.6, because the length is 5 and I just divide them by 5. For this case, I end up with 80, 60, 60, 45, x2 is 0. So I can simplify this too. And x2, which is my v2, is 3 minus 4. And when I normalize them, I get 0.6 minus 0.8. And notice that these two, they are orthogonal as expected, because this one lives in the null space, and the null space is orthogonal to the row space in this column. Okay, so we have the V, so we can construct our matrix V already. So let's keep that in mind. And now how about finding the U1 and U2. Now remember, our formula is what we used before is this one. But we have a problem here. We run into a problem that we have this guy right here. Our second sigma is 0, so we cannot divide something by 0, obviously. So there's a workaround to this, and I find what Professor Strang did in the lecture really enlightening, that he just grabbed the basis vector in U. So we remember, we want to remember again that U and V. So this is U is the orthogonal vector in the column space. So we have our U1. So just forget about this. And to find, let's name it alternative. To find U1 and U2. So okay, we only have rank 1, so we only have like one dimension in our column and in our row. So in terms of our column, we have this 4, 8. So imagine that we have a subspace that only consists of the 4, 8 line, and when we normalize it to a unit vector, it becomes 1/AT 4, 8. This becomes 4 squared 5 1, 2, and this becomes 1/squared 5 1, 2. So this is our U1, we can say. And our U2 is something that lives here, right? Because the left null space we have here, the left null space is something that is orthogonal to this. So we have something also orthogonal to this one. So it's fair to say that anything, if I dot product with this vector equals 0, so that will be my vector in the left null space. So it's safe to say that this vector right here, let's give it -2, 1. Or let's just make it same as what the lecture. So actually this is also equal to 2 - 1, but this is what I will use because it just, you know, it's just a line, it's just a different sign, so it doesn't matter. It's still in this subspace, right? This U2. Okay, so we have the U1 and U2 here, and we have V1, V2, we have sigma, so we can construct our matrix. Let's give it some space here. So A equals U sigma V transpose, U being 1/√5. The first one 1, 2, 2 - 1, and the second one is this guy and 0, square root of 1 to 5 and 0, and the other one is the V transpose. So let's see, V1, I want this transpose V1, and then the second guy here. This is, don't forget the minus here, just emphasize minus. 0.86, 0.6 minus 0.8. So this is our factorization of singular value decomposition of A when A is a non-full rank matrix. And this proves that this SVD is also works for the case where A is singular. Okay, a little thing that I want to mention, that you see here that even after our rigorous computation here, we end up with V1 0.6.8, which is initially we get 4.3. So this is actually also here, our row space, our first row in the row space. So what Professor Schrank did in the lecture is that he just skipped all this computation, and then he just grabbed this first row vector as our orthogonal basis in the row space, and built the orthogonal V2 from there. So that also works, and this method, the usual way to find V, also works. I just want to prove that both approach ends with the same result. Okay, and one more last thing, but let me delete some of this. So I want to point out that in the SVD, it's also helpful to look it in this form. So you see that we have this first column times the sigma times the row. So if I put that into some general form notation, then I have this, right? I have my first U1, the first column in the U matrix, and I multiply it by sigma and times the row vector. So this is column times row vector. So I will end up with a matrix. And then this is the second one, the same thing. So column times row, and this is all rank 1 matrix, right? So column times row of rank 1 matrix. And this is also helpful to acknowledge also this is the fourth way to multiply matrix. I just think it's beautiful that we look back to our previous lecture, in the initial early lecture, when we learned the four way to multiply matrix, and this is taken place here in the SVD. So I see it as a way that this will be our first metric. It's like our first layer, I would say, first layer. And then this second guy is our second layer. And each has rank 1, and then, well, of course, in this case, it is 0. So this will be rank of 0, but in case of this is a full sigma matrix without non-zero diagonal element, then you will see that this forming into this layer, and then it's just helpful to connect this into our earlier theory of the fourth way to multiply matrix, and this is used in the SVD. So that's it for the SVD. I will probably come back with a few more examples, and thank you for listening.